All right, we're going to discuss some information in section 9.4 of your books. Um, First, looking at what we call moment of inertia. Not just regular inertia, but moment of inertia, sometimes also called rotational inertia, symbol uppercase I. Now, here's how this number one differs from linear inertia. Way back when we learned about Newton's laws, we discussed how linear inertia was simply dependent on an object's mass, and that's it. We didn't even have a symbol mathematically straight up for inertia because inertia was solely tied to mass. So in linear equations, mass itself is directly tied to inertia. Um, Example, if we lift a bowling ball straight up, it's a lot easier to do than lifting a ping pong ball straight up. Linearly speaking, inertia only cares about mass. Now we're looking at rotating objects now. And there's a difference. Mass is a factor, but it's no longer the only factor. In class, we recently looked at a quick experiment where we took two objects, a solid disk, and yes, this ugly shading represents my solid disk, and a hollow hoop. The disk had mass m, and so did the hoop. They had equal masses, whatever it was, doesn't matter. Noting their equals what matters. And they had the same radius, we'll just say generically radius r. But something strange kind of happened when we rolled these two down a hill side by side. Every time we did it, the disk right here was the winner. So that leads us to a conclusion that as far as inertia goes, we got something different going on during rotation. If this solid disk of the same mass and the same radius of the hoop wins every time, well, mass can't be the only factor. Because if I linearly toss both of these up in the air in the same fashion, they'll be just as hard or easy, however you look at it, to move those things straight. But when they rotate, there's an extra factor involved, and that's what we call moment of inertia. Moment doesn't represent time, it represents positioning or space. Or in other words, it represents how mass is distributed. So moment of inertia is about mass and its distribution. And when we say distribution, we really mean distribution from the axis of rotation. So that's what we're focusing on. That makes things easier or harder to rotate on the axis of rotation. Now obviously with these two disks being like wheels rolling down a hill, the axis of rotation is in their direct center. And some formulas, which you could actually look up in your textbook because they're basically core formulas for disks and hoops, we could see a difference between them. So I means moment of inertia or rotational inertia. And looking up in your textbooks, we could find that the formula for moment of inertia of a solid cylinder, that would be considered the disk, with uniform mass distribution is 1/2 mr squared. Whereas when we look up the formula for the hoop, it's just I equals mr squared. So from a mathematical standpoint, the moment of inertia for the disk is half as much as that as the hoop. The higher moment of inertia an object has, in this case of comparing these two, the hoop has the higher by twice as much. The harder it is to start it to rotate, or on the flip side, to stop it. That sounds a lot like Newton's first law, which it really is pertaining to. An object in motion wants to stay in motion, an object at rest wants to stay at rest, which we also call the law of inertia. Here we would really call it the law of moment of inertia. Saying just law of inertia means linear fashion. Linearly, yes, mass is all that matters, but rotationally, then we got to look at mass distribution affects it. So this one will win every time as long as it has the same m and r. It has less moment of inertia. Now an example that you on your own could do right now is to grab your textbook and use some formulas given in the book to feel this effect, basically. A textbook can be considered like a rectangular plate. So we have a textbook or any object rectangular in shape that would maybe be like a textbook, and we rotate it in two different fashions. If you grab your book and place your hands here and here, opposite of each other, you're rotating an axis that is down central through it. And that means a lot of the book's mass on this side and on this side is fairly close to this axis of rotation. So grabbing a textbook and rotating it with your hands here and here and flip-flopping it around, this will have a low moment of inertia, at least as compared to if we grabbed the same textbook and grabbed it at the end. If we grabbed it at the end and made this the axis of rotation by putting your hands here and here, now we see all this mass is distributed away from the axis of rotation. More mass is distributed away here than here. That means in this case it would have a higher moment of inertia. You will directly feel that it's much harder to rotate this book when grabbing it here than here. So it's not just about mass, because obviously this book has the same mass if you're using the same textbook in each case. It's about mass and mass distribution. That's what matters. That's why mass and either a radius or a length of an object is going to be involved in all our formulas for moment of inertia. Now, generically speaking, here are some formulas that for finding the moment of inertia. Sometimes a system might have several objects connected together. Therefore, the moment of inertia formula for a generic situation is the sum of all the moments of inertia of every object. So we could call, say, mi as a summation ri squared. And this is considered for a point mass, which we'll discuss more in class. And what that really means is just summing up the total number of masses and their moments of inertia. Mr squared is the generic term for a point mass. Again, we'll discuss that more in class. For typical objects like rectangular plates, rods, cylinders, spheres, things that often are rotated, you could find specific formulas for them in the book. If it's an object we could treat as a point mass, then we go through and sum up all their values. We'll do examples in class like that. That's the general formula. And moment of inertia is important for finding rotational kinetic energy. K meant rotational or kinetic energy, excuse me, before, and we'll just specify K rotational. Now, if you recall, linearly speaking, kinetic energy was 1/2 mv squared. And it's very similar looking now we define moment of inertia. Instead of 1/2 mv squared, it's going to be 1/2. Instead of mass in the formula, it's going to be moment of inertia. And instead of linear velocity squared, it's going to be angular velocity omega squared. So kinetic energy at any given moment is 1/2 moment of inertia, or again, moment of inertia is, just think of how easy or difficult it is to rotate an object times the angular rotation in radians per second. And it will still come out in a value of joules since it is energy. So those are the two core formulas we're going to apply in class to some example problems. But the main idea to get from this lesson is to understand that moment of inertia is how easy or difficult it is to rotate something. The higher number you get out for I, the harder that thing's going to rotate compared to a lower value for I. And to end, some practical applications of this some of you may experience on a regular basis. One good one I like to use is for those of us that are familiar with going to the weight room and using Olympic-sized weights that use these large bars, oversized bars that kind of look like this. On average, they're about 45 pounds and probably pushing 7 feet long, 6 to 7 feet long. And they look like they have these big collars on the end. And not only that, the weights are oversized too that you put on these, and they're very large. And one good question to ask that you may have never thought of, why in weight training do we often see these big oversized bars with big oversized weights? And the answer we often get to that is, I have students say, oh, well, that needs to be a big bar because if it's a small bar and you put a lot of weight on the ends, then it might bend. To a point, maybe that's true, but that's not really the focus of this thing. A, a steel bar is very strong, so a thinner one could hold many hundreds of pounds just fine without worrying about bending. The real reason we use a big bar, and this is a horrible drawing, but a big oversized bar as compared to like a little home gym that might have a skinny, not as long bar, not as big weights that go on it, is this one would have a much higher moment of inertia. Think about when you're bench pressing and maybe you lose a little control and your arms start to kind of fight with the bar, and the bar starts to rotate around its central axis if, let's say, your hands are here and here. So the point of rotation is at center. A larger bar with oversized masses distributes the mass far away from the central axis of rotation. That's what gives you a greater moment of inertia. Now, if you use a smaller bar, central axis is here, but now the mass is only distributed maybe this far away, giving me a much lower moment of inertia. What happens there is this bar rotates naturally much more easily. So typically you could lift a lot more weight on a Olympic size bar because you're not worried about wasting energy for control. On a smaller bar, you're using a lot of energy to fight that rotation, which means you're not going to focus most of it on lifting this weight up is what you want to do. And we'll give many more examples in class.